Now you can start. We will get this notification. Okay, Minoo, go ahead.
Okay, good day, everyone, and thank you for joining me today. In this lecture, we will going to discuss one of the most powerful object detection algorithms currently available, FastRCNN. FastRCNN is a state-of-art object detection algorithm that was introduced in 2015. This is the paper that allowed for the first time real-time object detection framework called, as some of you know that. I think that it stands for you only look once, and that's actually we're going to talk about these kind of materials here today.
So, Minoo, the microphones that are picking up are there. So if you can speak to us, you will be speaking to the recording.
Yeah.
So speak up, but it's very hard to hear you.
Okay.
That's what I'm trying to say.
Actually, what was I? The yellow is originated from this paper, and we're going to go through the details in this paper, in this lecture. Before this paper, they realized that we can only separate object detection in two parts. The first part is that image classification, and the second part is to detect the objects that are in the image. And the most important and difficult part of this object detection is to create the hypothesis of what parts of the image are could be the objects. This is the outline of the lecture. We will begin by fundamental concept, discussing the problem that RCNN families were designed to solve, namely object detection. We will introduce RCNN, and then we will go to the FastRCNN, and finally we will get to the FastRCNN, which is the main goal of this lecture, and we will explore some key components of FastRCNN architecture, and we will dive into the details of how FastRCNN works. It's kind of a baseline of basic fundamental things about this lecture. In computer vision tasks, we have.
It's cute how you call this meeting a lecture, by the way.
Kind of for a main classic.
I think of it as a discussion, but
okay.
It's just cute.
It's the first one is classification, the classification and localization, object detection, and instance segmentation, which most of you are familiar with these topics. But here we are going to we're going to discuss object detection, and for a start, we will talk about classification and localization. So in the classification and localization, we need to localize where the objects are and then classify the object. So we need two classifications here. The first one is for classifying the object, and the second one is to figure out the dimensions of the box that we want to capture an image with. To evaluate the performance of object detection, we will use intersection over a union, which is known as well. And let's go briefly over the first two members of RCNN families of object detection architectures. The first part of
There is a question.
okay.
Yeah, I'm wondering how this relates to the medical imaging research.
Excuse me.
Yeah, can we use it in medical imaging research?
Yeah.
Can you motivate it a little bit,
Yeah,
why you chose this paper?
It's kind of related to my presentation and the work that I want to work in my class, actually.
Oh, so you're practicing for your class?
Not really, but
Okay. It's just good to know in advance that then the style is different.
yeah. maybe, because some of these concepts are unknown for me, and that's why I put them in the lecture for the fundamental
Yeah.
sections.
What is the class name? What is the class?
Image processing.
Image processing.
The first part of RCN, okay, where was I? It was, yeah, I was trying to explain RCNN architecture. The first part that we start our architecture is selective search, which is used to determine the regions of the image that should be captured. Some small areas are determined first, and similar regions are combined to create a larger Minoo region. This process continues repeatedly. Large regions are created at each step during this process. For example, here we have the image, input image of a woman there, and we try to localize where is the woman and where is the television. So we do some segmentation, and we reach to the point that we can actually find that.
Where is CNN there?
It's not, it's the beginning of CNN.
So
First we do the selective search to segment the parts, and then we try to
what is this selective search? Can you explain the first right arrow from the woman to that?
yes, from that input image, we're trying to find the similar, we trying to capture the pixels that are they are similar to each other based on color, texture, or something like that, all of them, and then we combine them together to get another bigger segmentation, because some similar objects close to each other are related to the same subject.
You may have said this, but does the R stand for recurrent? Is that what this is, like a recurrent CNN of some kind?
Yeah, kind of. It's a repetitive.
Okay, so it's basically iteratively improving a segmentation.
Yes, yes.
Oh, but there is no CNN
This
here.
is not a neural
This is
network.
clustering.
Yeah,
This
it's
is just
a
a
This is
different
clustering.
system. Maybe I labeled the
Yeah,
slide wrong.
They're gonna make it into the CNN.
Yes,
later.
exactly.
Yeah, this is clustering of pixels,
Yes,
basically.
that's right.
You can cut to the chase and run k-means, and you will get the picture on the right with appropriate value k. You don't need the intermediate steps. Okay, if you run k-means on your colors, RGB, you will.
Yeah, but this is probably like a more sophisticated like visual algorithm that they use like during image processing. days.
Yeah, but what Minoo says is just grouping by
Yeah,
similarities.
but I think it's like
Yeah,
more like
it's
a
a-
watershed based, like there's a lot of these kind of like more
So
visually.
proximity.
Yeah, those types of ideas.
Some kind of.
And now we're going to the RCN architecture. This is a full diagram for RNN input from the selective search. Selective search identifies candidates for specific regions. Each region's candidate is given as an input to the different CNN network. As a result of this operation, approximately 200 different regions are obtained, and 200 different CNNs are trained here. And at last, the class of objects are determined with SVM and using the features from these networks and bounding boxes of the objects.
So when you cluster the pixels, they are not clustering into boxes. How do you obtain the boxes, the rectangular shapes for the input to CNN, each of them?
A selective search does that for me.
What is
The output
selective
of,
search?
this is
selective search.
And the output of the selective search is the rectangles.
Rectangles.
Around.
Oh, so there is a pre-existing algorithms that results in the
Yeah.
rectangles. Okay.
But the cost of RCNN models are quite high, because nearly 200 different candidate regions are extracted for each image, and different CNN networks are used for each region. This process steps cause both a great cost and long training time, obviously.
And I think also one of the issues is that there's no flexibility in the number of like proposals, like you have to kind of set
Yeah,
it beforehand. So if there's like a million objects, you're never gonna find them, which obviously a million is a little bit much, but.
But so you set the hyperparameters and gives you exactly this number of.
Well, it will find that or less generally.
But what happens next? I don't understand, because it says SVM, but who goes and manually labels each box because the images are different? Like,
With
how do you?
Cocoa or something, they probably use a Cocoa, so you have like the overlap between the box and the class for the box.
Oh, so each box is actually labeled by someone,
Yeah.
training.
Cocoa is like a data set with liquid model. That's generally what they use for these models.
So each data set is like, each box is labeled, right?
Yeah, you have like a width, height, and
And the
location,
label.
and a location and a label.
So Mohammed, for the cell selection, also you have this bounding boxes, somebody manually created them and labeled each cell by cancer type or whatever?
Yeah, it should be actually trained in some way in the beginning.
Yeah, like you need the labeled, human labeled data then. Okay, got it.
Right.
Yeah.
So because it has its own issues and problems, they developed another architecture, which is a fast RCNN. In fast RCNN, different CNN models created for each region in the RCNN architecture were removed, and fast RCNN architecture was developed using a single CNN for regions. At first step, as I mentioned, it processes all the image to extract the features with the CNN, and then it uses other layers to project the map. Yeah, I should explain more that. Okay. So this bounding boxes is projected. After that, they created the bounding boxes. They projected on the feature map, and this way, this is named ROI projection, which means that region of interest projection. And then they connected to the fully connected layer, and they extract the linear and they extract the bounding box, and they label it. Actually, we should think about this, about the neural network, that it has two heads. The first, which we train a model on that, and then we use the two head of this model for regression and classification. For one of them for regression and one of them for classification. That's what you can see in the top of the image here.
So if you are combining fully connected layers of 15 objects, what does your softmax classify? I have 15 objects in my image, right? 15 types of objects. They all have different label. Let's go with 2. So what does linear plus softmax? What does fully connected? Before it was kind of clear, and we Cocoa data set, each box has a label. But here now you're like, okay, each box has a label. I understand you have this isotropic network, whatever, it doesn't change, it's the same size. And then you're like, okay, let's just merge everything. And now you, after this FC, you don't know anything about the location because it's permutation invariant. And what are you predicting there?
I extract the bounding boxes around the images, and then I train the model based on them.
I think what you're
Well,
asking,
linear is fine, but classification.
I think the idea is that you pool, and for each region of interest, you predict the label, which can be 0 or all the other labels. So it can be nothing or something else. And then you predict the bounding box for these regions of interest from a proposal method. That's how you, yeah.
I don't get the 0.
So
Can
you
you
have-
explain the 0 against once
So
against? one?
sometimes like a region of interest doesn't actually contain an object, right? Like there'll be like a region of
Oh,
interest.
so you're looking for just one object here. So
No,
that's
for
a-
multiple, but like you have multiple regions of interest, but that's like a kind of a coarse approximation of like the actual objects in the image. So you can see here, like there's regions of interest right after the ComNet. And for each region of interest, you predict what class of object is in that part and where the bounding box is.
But not when you apply fully connected network to their combination, those arrows that go like that.
Yeah, but that's for pooling for like a global feature that you also use. So you use a global feature and the region.
No, so there is another classifier that exactly the same as we were doing before on those underlying boxes on each of them.
Yeah, so the way I think is good to explain is like YOLO came before this. And the idea there was that you have a backbone convolutional neural network. And then after like 5 layers, you have like, let's say 9 pixels, similar to like Alex's network where you have like these convolutional maps. And they represent some sort of region, like they represent some perceptive field in the image. And then just for each of those, you predict a bounding box and a class.
And class, but the
Yeah.
fully connected network is something else. Well, what I'm confused by is the softmax. If we only want to teach the fully connected network to predict those bounding boxes by regression,
Yeah, but each bounding box has a class, right?
but once you pulled all of the bounding boxes into a fully connected network, you lost.
Yeah, but I think you do the fully connected network only, you do it per region of interest, I think.
Oh, so the picture is wrong. Okay, per region, I understand it's the same as before and it works perfectly.
I think, right? Or
I think that they use max pooling to actually reduce the dimensionality of the data.
No, max pooling is fine, but the fully connected network, when all of the regions go into fully connected network together and the fully connected network combines it, then like everything is combined. All of the classes are there. All the possible classes that this image contains are there. So what are you softmax predicting? You're doing like a binary encoding. All of the images that are there should be higher than all the classes that
I
are.
think what you're trying to say is that you have a combinatoric problem.
Yeah,
Like,
yeah,
you have
like
an infinite number of classes almost that you could predict, which is like, there's class 4, 3, and 1.
Yeah,
Or
yeah.
class 3, 2, and 1, or class. Like, you just-
Well, but even then you don't know which class is which. After
Right, no,
fully
exactly,
connected.
yeah, that's fair.
That's yeah. Like if combinatorics problem, we can ignore for now. Like,
Right.
have a single person.
And this is the comparison between the RCNN and fast RCNN.
So I mean, still, I don't understand how anything is predicted from here in terms of class. I understand you can learn bounding boxes maybe, but the slides do not explain how you train it at all. The left one is perfectly understandable, but the right one, like you're trying to skip quickly, but no.
I want to go to the faster RCNN because it's much more related to this. Maybe we can find the answer there. That's why I'm trying to quickly go over the rest.
Yeah, okay, but right now, like, it's this.
This kind of reminds me of like the YOLO algorithm a little bit. This
Yeah.
is like,
It's the
Well, that's what Elo is saying.
Yeah, it's based on the.
yellow will be the final stage. So in the faster CNN, the faster CNN was, I want to mention something here, and it's a faster trainer because we just use one convolutional layer and not lots of them for extracting features.
I think what maybe it is that they do pooling to determine which of the ROIs is good. I think that may be what it's doing. I think
Only
Alex
one-
also said that.
I think only one region of interest will be picked and will be fed into the.
No, but there's like a lot of bounding boxes in a region of interest that could be correct. I think they prune it. That's the same thing they do for YOLO at least. I'm not sure if that's also what Alex says, but. In the chat.
so that is-
What does
He was talking
pooling
about
mean?
multiple bounding boxes.
What does pooling mean?
Pooling is one of the operations that COMNETs sometimes do.
But also if you, let's say you have an image, like an object right here, like in the image. You can have like a million bounding boxes that could capture that one thing,
Yeah.
right? but you want to have the one that is the most form-fitting around it. So the way that's kind of what they mean is like pool, I think pooling is like, you pool it so that you have like the best bounding box around that image, around that object. Does that make sense? Like you have like 1,000 proposals, which are all capture it, but the one that is the most form-fitting around it is the best bounding box, because otherwise you don't have. I think that's what they mean by pooling here. I mean, that's also what they do for YOLO.
Strictly speaking, it's like, like a convolutional operation, kind of like a convolutional operation where they take the max value of like filter size in that region and throw out everything else.
It doesn't have to be, just averaging is also.
Yeah, okay, I think we were.
Well, you're describing different kinds of pooling.
Yeah, I was
Yeah, I
given
remember
the
this.
2-second version.
Oh, yeah, okay.
So I don't even
Yeah.
know if they're talking
Yeah.
about that specifically here. I
Yeah.
think they're actually talking about pooling the bounding boxes in a region of interest. But yeah, we can continue. I think faster CNN also make remember sense than faster CNN. It was like an in-between network that wasn't that good.
The architecture of faster CNN consists of two main components, the region proposal network and the faster CNN detector. In this paper, they realized that actually detecting the object is an image and then classifying those objects are similar tasks. So probably they can share most of the weights in the neural network by sharing the weights. Not only they get joint optimization, they get actually the better results as well. They didn't do it before this paper, I guess, or there are few of papers was doing it. The paper is pretty much all about the region proposal network, and which is the part of a whole system that detects where the objects are. The image is first passed through the backbone network to get an output feature map, and then the ground truth bounding boxes of the image get projected onto the feature map, and the backbone network is usually a dense convolution and network like ResNet or VGG16 or ZF. The output feature map is a spatially dense tensor that represents the learned features from the map, from the image actually.
Hey, Alex, could you put any links to papers inside of Slack, the reading group that you're putting in the chat?
Are you talking about YOLO 2, Alex?
Can we not have sound?
Put this.
Oh, yeah.
Spatial pyramid pooling, oh, yeah, 2015. I thought it was Eric's.
It has 55 total citations, this paper. Almost. And if you want to compare it with fast RCNN, both have input image, it passed into the convolution layer at once, and we got a feature map. But the projection on the feature map was from selective search when we have the fast RCNN, but here we have RPI, which is a region proposal network. And because of this, it's much faster than the previous version of RCNN. So what is RPN is exactly, because the other parts are probably kind of straightforward. And the feature map that is generated from input image by the convolution and neural network is passed into the I said that actually. But
What does ROL stand for?
I think that's.
It's a regional,
Region of interest. Okay.
that region of interest bullet is actually the last layer that we classify objects with that. And because it's not a fixed size, the output of the feature map, we need to make it fixed size and then pass it to the output.
So can you go back? Same question. How do you train this? Bounding box regressor for each ROI. So ROI pooling is not ROI pooling, but ROI selector. So you
Well,
still
you
have,
pool within the ROI. That's, I think, the. idea.
but then you, like, once you created an ROI,
Yeah.
you're back to the step one.
Yeah, which is to do the.
One by one, you just.
But instead of doing it before the convolutional neural network, you now do it within the convolutional neural network, and you share features because you use the feature maps to train an RPN, the region proposal network, which is a small other convolutional neural network that does the prediction of the proposal network. So you have one backbone which generates the feature maps, then you project the region proposal onto it, and then you use that for ROI pool.
So then basically then you get as many heads as you have finally regions, ROIs, and you just flow the, but what happens inside of RPN? It's an end-to-end network, so there is no training signal there. It just gets the gradient from a second.
Well, from the ROI pooling afterwards, right?
Well, it's just the gradients only come, or the measurement, the loss is on classification, only on the left red.
And the
box.
bounding box regressor, right? Because that is the target you have also in the image. Like the way you should think of Coco is like you have, like, let's say 10 bounding boxes with a label for each bounding box.
Yeah, but still they come from that rightmost block.
Yeah.
So there is another red block, but it's confusing. There shouldn't be a red, like there is no signal there at all in the green in RPN. RPN has an input loss, its own loss separate from the.
I don't think so, no.
Yeah, so it confuses me, but now like other than like.
When they say for each spatial location, by the way, they just mean like for each feature, right? Like spatial location of the feature map.
Yeah, right. That's but
Yeah, no, I know. I'm just saying.
So it's still kind of, yeah, the head is parameter tied, so you have exactly the same head for no matter how many bounding boxes happened in this specific image.
Right.
And so you're doing more averaging, like getting larger patches, etc., stronger gradient signal. Okay. This one I understand how to train, but fast RNN I don't understand how they train. Like the pictures, there's a CVPR diagrams, they cannot just, I don't know.
Well, it was also funny because fast RCNN came right before YOLO V2, which completely upended the whole fast RCNN. I think nobody ever used it really because it was like the year after that YOLO V2 came, and it was like I think 100 times faster and also better. And so this is kind of their response.
Oh, faster RCNN was.
Yeah, it's
and
like,
are they?
But YOLO V2 was better.
Well, but the speed up is only in parameter sharing, like it can train faster and
Mhm.
et cetera, et cetera.
Sure, but also you need real-time object detection, right? You need inference to be super fast. It's funny because I feel like YOLO had way more of the actual interesting ideas, and they just had to kind of iterate on them. But faster RCNN does have a higher accuracy than YOLO.
Oh, faster RCNN.
Like this one has a bit.
But I don't see, like this became more complicated than the original idea than for object detection. Oh, because in the original idea, you have that old school algorithm that is slow. Yeah.
And also hyperparameter and stuff like that,
Yeah, because like this is a complex network, has too many pieces, so for inference, it will be slow. Like,
yeah. Yeah, but it's all convolutional layers except for the last part, right?
Yeah.
So that's why it's super fast. But in YOLO, you only have, I think, convolutional layers, which is why it's even faster.
So people observe and practice that faster, like this thing is faster than YOLO.
No, so this one is not faster. but it's better as hierarchies.
Oh, all right.
Yeah, it's kind of funny because the YOLO author actually stopped doing the research because he said, I don't want it to be used for bad things.
I didn't want it to be what?
I don't want it to be used for bad things, so he just stopped.
Wow.
It's also funny, if you read his papers, they're very like, just very professional.
I wonder if he's thinking about drones. I mean, like if you were using this for the drone program, maybe it's.
Right, so he was like, I'm
Anything.
stopping by.
Yeah.
After I think V2 or V3, he was just like, yeah, guys, I'm out, bye.
Or jaywalking detection.
And this is the anchor boxes that I go through the details here about the anchor boxes that they use for object detection. They don't just using the sliding windows, they use anchor boxes and they their input are a feature map. So it minimizes the computation and it makes it more efficient. That's another reason that this paper is more efficient than previous papers. And they also, the really good thing about this paper is about the logs function that they developed. Because they want, they want to recognize classify the image if there is an object inside it. They develop this logs function, which is
So
It has
they
two
is
parts.
which of the three papers?
it's for faster RCNA.
And it's not, it seems to be, should be in the fast RCN as well, right?
No, it's not.
Where is the multi-class classifier in this loss? If you go to the picture or to the diagram, there is a multi-class classification and
Yeah.
object regression. Yeah, so multi-class has just additional class for not objects.
And the gray. The box regressor is for that section.
Yeah, box
And,
regression is fine, but
And yes, and this, they didn't classify the object on that layer. They want to just, it's a binary classification. They want to know that is there an object inside that image or not. If there is, they draw the bounding boxes and they minimize it. But if it's not, they just pass.
what, so this is a loss function for some model. Can you go back to the model diagram?
Yes, this is the model.
Yeah, which model on this diagram this loss function applies to?
The convolution and neural network RPN. This the
Just the RPN?
Yes,
Oh, so there is a separate loss, so so there is the multi-class plus bounding box regression, and there is object classification plus bounding box loss, so there are two losses there which are virtually identical. I would just train it end to end, I wonder.
Yeah, that's what YOLO does, that's why it's faster.
Yeah, like the class, the last class will be non-object.
Right.
That's just, that's it. But oh no, well, but what Minoo is claiming is that, that's what he said, that those which are non-objects, they will not make it to the next loss.
yeah,
Yeah, that makes sense.
So you're kind of, okay,
is it wrong?
No, it makes sense.
we're trying to figure out.
And this is the loss function.
And where is the other loss function?
And they just.
Yeah, this is for RPN, so you
Yeah.
should have your slide loss function for RPN part. Or something like
This
that.
is for RPN part, they didn't mention the other part, I think.
Yeah, but your title, like just giving you hints for your presentation in the class, the title should be better.
Yeah.
Not a loss function, but loss function for RPN part. RPN is a part of the thing, the whole thing.
And this is the results of 3 algorithms. They had, this paper had a really long results section. I just bring you here the highlights, which compare the speed and MA of it, and it shows that how fast they get. This is a sample of which they have in their paper.
If they go even faster than this, because it's still not real time, I think.
I think it's real.
Well, then it would have to be 1/30th of a second, right?
200 milliseconds, yeah.
It needs to be, because if you now multiply it by 30, it's gonna be 6 seconds.
Okay.
Like FPS, like frames per second is generally at 30. So
What is it called when your eye gaze like jumps around a lot and like the you know what I'm talking about? Like
Saccades,
yeah, I think so.
saccades and microsaccades.
Yeah, I mean, like, it kind of reminds me of like in my domain, there's this thing called cube sampling where they, instead of like doing convolutional operations over the entire MRI, they do like just near the surface. It seems like I wonder if there's any way to do this algorithm with like a subset of the convolutions and like optimized in such a way you don't have to do as many. Similar to the way we trace our eyes around things. Like we're not processing all of it.
Yeah, you need to first heavily low pass the image still to know where to compute the trajectory of like interesting parts, right?
Mhm.
Because otherwise it's kind of a chicken and egg problem if you're just working with the image. You need to decide how to trace the image. For that, you need to look at the entire image. But you're already looking at the entire image, I might as well just do it with the segment. But if you have like a low pass filtered tiny image, oh, okay, now I'm faster at what you're suggesting. Yeah, and like it's an interesting suggestion. I'm just trying how to make it.
Mhm.
I think what they do also here is everything in parallel, right? So every single region of the image, because it's a convolutional neural network, you can do everything in parallel.
Yeah, it's just, it would be a memory saving, it would be probably time saving.
Yeah, that's fair.
So when are you presenting?
So one second. Next one.
Yeah, okay, so what do you have any other questions? Any questions? People online? Any suggestions for Minoo with her class? How should she improve the presentation to get the better degree,
I
better?
probably will use the first part
Great.
of the lecture in the class. And not dive into this neural network details of it.
Why? That is the interesting part, right? How it works.
Yeah, but it's not related to image processing, that function. The selective search part may be more related.
It is
Neural
image
network
processing.
part.
That's the only way image processing will be done in the future.
I think Mina have to describe kind of draw a whole schematic of the system and then describe each building block and why we need it. And then she can also like read the 3 papers that was compared, like fast RCNN and then fast RCNN, and then she will see like that fast RCNN is actually not that different from fast RCNN. The only difference is that they added region proposal networks that use convolutional layers at test time and they shared. So like basically switching from linear layers, they switch it to CNNs. And this is like the main benefit. And I think if you like understand the building blocks and have this like scheme of the system, you will understand it better and will explain it better. Because if you don't actually know these building blocks, it's really hard to understand for people, I think, why it works. Because I noticed that we have a lot of questions from Dr. Please, like from others, that they just don't understand the building blocks. Then kind of you'll explain better and not just kind of gives us like additional feelings that you need to read more.
Yeah, so basically your suggestion is for me to understand each building block, what it does.
Yes, maybe like start from overall like general schematic. Like we have this black box and this is input, this is output, and then we have this black box three different implementation, for example, the slowest, the fastest, and the fastest. And then maybe start from slowest, that will explain this black box system that is like beginning general thing, and then how we can improve it by, for example, moving to faster CNN, and then how we can improve from.
I like your suggestion of taking a step back. I would take 2 steps back, and I would start with why we need object detection. Like William wants to build drones, things like that, right? So like why we need to make it fast? Like just motivate the question, or like what is being solved? And I'm joking, but yeah.
Yeah, it can be like vision, like she can put like vision slide, like kind of perspective vision, and then she might say news, oh, we can do this thing that fast. And then she can say steps. What are actually steps? Like she can describe these 3 different.
Yeah, low power devices, why we need it faster, like.
Yeah, this is vision, but news should be like, we can do this now, that fast, and then maybe steps, it will be the whole system and like building blocks, and then she can go on faster CNN, like, and then faster CNN, and then kind of, maybe if you structure this way, I think it will be much better for class.
Oh, for class also, what is missing is what Eloy filled in for me. You need to show the Moco dataset. We have this training dataset labeled like that. Remember, like in machine learning class, I'm asking like that's essential knowledge. How, for me or for many people, to understand how it's trained, we need to know what it's trained on. And you need to show, okay, here's the dataset of Coco. Yeah, Coco dataset, like each bounding box is labeled, you have this coordinates given and a class given. Show some examples, not in the end in the results, but in the beginning, this is what we train on. This is our ground truth signal, that's where we get it. And tell where it came from. Maybe it was labeled by another computer vision algorithm. You will get bonus point for the class that, you know, training data was created by a computer vision algorithm or something like that. Or by people, then you don't get bonus point. But to add that, and it will be clear, I think. And the headers of your slides are confusing. They kind of don't relate to what's on the slide often, and this is confusing. Loss function. But yeah, thank you very much. That's thanks everyone for coming, and well, let me stop the recording.